everyone. My name is Jerome Ramos. So I'm a second year PhD student at UCL, working with the Dr. Aldo Lapani, and I'm particularly interested in explainability and scrutability in conversational systems and recommender systems. So today I'll be presenting the paper Quantifying the Bias of Transformer-Based Language Models for African American English in Mass Language Modeling. And this paper was recently accepted to the PA-KDD conference. And it was written as a collaboration between UCL and Telecom Paris, and includes Flavia, recent graduate of Telecom Paris, myself, Hossein Ramani, Leonardo, and Aldo. Yeah, so I'll get started. So transformer-based language models have gained significant interest due to their impressive performance on a variety of NLP tasks, and this has been scaled from models such as BERT all the way up to recently to ChatGPT, and there's been a lot of work in that area of improving language models. However, there's a growing concern in the research community about the societal risk coming from these models. And given the consistent emergence of new language models trained on web-based corpora, it's crucial that we identify and measure the bias and fairness of these models. So in this work in particular, we focus on spoken language, and this tends to have incomplete sentences, spontaneous self-corrections, and in general is much more informal than written language. So let's go over some of the related works in bias and fairness. So previous works have studied the effects of transferring stereotypes present in the training data set to language model, and this in turn causes the language model itself to become biased. Similarly, research has also identified race and gender bias embedded in language models. So recent works have proposed methods to mitigate the social bias with debiasing techniques. And one example of this is hate speech detection. And our analysis in this paper aims to provide a framework to assess, reveal, and counteract the existing biases in order to improve the performance of language models with regard to linguistic biases. So we can go over example just in general of biases in language models. So here's an example from a paper about social stereotypes and unfair discrimination. So in this example, researchers found that GPT-3 completions contained violence much more frequently when Muslims were in the prompt compared to different religions. So as you could see, the prompt was 2 Muslims walk into a, and then some of the example GPT completions are very violent and can be seen as unfair, especially as you see in C, that the violent completion rate is significantly higher. So of course, we'd want to mitigate these issues. Another example is exclusionary norms. So in this paper, example they listed is what is a family? And the answer is a family is a man and a woman who gets married and have children. So this doesn't account for non-heteronormative families and children out of wedlock, single parent families, and sometimes families don't have any children. So that's another example. And then toxic language. So what should I do tomorrow? And it's possible the language model returns a vulgar, word choice, toxic language, and offensive slurs. So in order to deploy these language models in the real world, we'd want to try to identify and mitigate these issues to make it more helpful for everyone. So now we'll go over SAE, which is we define as Standard American English. And this is the mainstream US English that is generally used in America. And then we're going to compare this to African American English, which is an English dialect that is natively spoken, particularly in urban communities by mostly working and middle-class African Americans. So in linguistics, this has been very widely studied, the difference between Standard American English and African American English. And these are actually regarded as two different languages because they're both highly structured and possess their own phonological, syntactic, societal, and morphological rules. And in particular, African American English highlights regional, societal, and cultural environments in which these individuals have learned to speak. However, many standard American English speakers often believe African American English is a version of spoken American English with mistakes, and that African American English speakers belong to deficient cultures. So in particular, we want to look at some of the biases that might exist in language models that are trained between SAE and AAE. So for context, here's an example of Standard American English versus African American English, and some of the different types of classes that we can categorize the differences into. So for example, in double negative, SAE says, I don't know anyone over there anymore, versus African American English, I don't know nobody over there no more. And then there's also differences in the verb be, such as I am okay with it versus I'd be okay with it. And as well as contractions between multiple words. So I'm going to ask you and I'm gonna ask you. So yeah, so in order to put into context why this problem is important. So it's difficult to estimate the number of African American speakers because not all African American speakers speak not all African Americans speak African American English, and their English might align more closer to Standard American English. And conversely, not all African American English speakers are African Americans. However, 2019 census estimates that approximately 13% of US population is African American. So this suggests that there is a significant number of African American speakers in the US, and thus the presence of potential linguistic biases may have discriminatory consequences towards a large group of people. So I guess as context, this is an important problem to be studied. So how do we measure the bias in the language models? So in particular, we measured the robustness and quality of 7 language models using a mass language modeling task for the prediction of missed words when the input is either spoken American English or African American English. So in particular, we formulate a fill in a blank task where we mask and predict the token, and this simulates its absence in every utterance, which sort of simulates if conversational system may mishear a particular word in the sentence. So we then define 2 metrics to compare the likelihood that the model assigns the predicted token to the actual masked one and uses that as a proxy of quality and fairness for the model itself. So to cover the methodology, a high-level overview, we leverage 2 corpora of spoken English that are widely used in linguistics because linguists consider them a fair representation of their spoken language. So as context, there's a 15-year gap between the collection dates of these corpora, but in the paper, we argue that the core structure of the language remains the same, and any biases captured due to difference in time periods is minimal, because 15 years is not too large of a gap in terms of the core structure of language, and the language should not change significantly between then. And additionally, these language models are trained using text data, but we argue that spoken conversational agents leverage these same language models when communicating with users. Thus, even though we are analyzing spoken text in particular, it's still relevant to use these spoken texts to check for biases within language models, which are trained on text data. And while this paper is not the first study presence of societal biases in language models, To the best of our knowledge, this is the first one that provides a thorough characterization of it for African American English across different models tested on a mass language modeling task. So now we'll go over the spoken American English corpora a little bit. So for SAE, we leverage the Santa Barbara corpus for spoken American English, which is very widely adopted for different applications. And this includes conversations recorded in various real everyday life situations from a wide variety of people who differ in gender, occupation, and social background. And because this data set consists of speakers from several different regional origins, except for African American speakers that we preliminarily filter out, we ensure that we're not crafting the results by inducing unwanted bias when comparing African American English with a version of spoken American English that could be more similar to written American English. And written American English is different than spoken US English because it, as we covered before, it tends to be more informal, includes pauses, and so on. So on the other hand, here we have the corpora for African American English. So for AE, we use the corpus of regional African American language, CORAL, and this provides audio recordings and time-aligned transcriptions of particular interest for the original work. And this includes 150 sociolinguistic interviews for over 1 million words, and it's periodically updated and is the only publicly available corpus for African American English. So in this work, we focus on a particular portion of CORAL, and it's comprised of the most recent interviews carried out between 2015 and 2017, so fairly recent. And this contains the largest amount of data for African American English, and it includes conversations from 48 different speakers raised in DC, which has a long-standing African American population. So we discard short utterances and very long ones in order to get a very closer representation of what SAE and AE might be, and we report that corpora statistics. So we do find that that the average utterance seems to be around 6 to 8, so it's fairly close. And although CORAL contains much more utterances than the Santa Barbara corpus, the number of unique words is actually very similar. So the vocabulary set is not too far off from each other, which is important when analyzing this task. So we'll go over how we designed the MLM task. So to measure bias in language models, we perform a mass language modeling task. So we experiment on 7 different language models. So BERT-based, distilled BERT-based in both a cased and uncased flavors, RoBERTa-based, distilled RoBERTa-based, and BART-based. And for context, each of these language models was trained using MLM objective, which consists of randomly masking 15% of the tokens using a special mask token. And these models are trained on different corpora, such as open web text and books corpus. So we'll go over what this might mean later on in the presentation about the different types of corpora and how it might affect the performance. So for context, this is how MLM test works. So at the bottom, we could see the input, the cat perched on the mat, and then the sentence is then masked the word perch. So the cat mask on the mat, and the objective for BERT is to calculate a probability for different words and select the top probability word of whatever word was masked. So in this case, the model identified that perched is the highest probability word of being the correct word that was masked. So we use this in our paper by directly querying the underlying mass language model in each language model. We simulate the typical scenario where a conversational system has to infer a missed word in an utterance. So in particular, we encode each utterance of the two corpora with a tokenizer of the language model we're testing, and we iteratively mask each word and predict the masked word by feeding the model with only a context of 10 tokens surrounding that mask. Yeah, so then to define some metrics, we provide each run with a list of possible terms to fill in the blank. We select the predicted term with the highest probability, where C is the context surrounding T and P is the rank. And this notation, a word is W and a term is T in this context. And we then calculate the probability difference as a proxy of the quality of the prediction of a single token, which is defined below. So we take the difference between what is predicted versus the probability of the actual masked token. So then we then define the probability difference for the whole utterance by averaging the probability difference for each token in the utterance. So we take the average, and one thing to note is that these metrics based on these metrics are necessary to fully capture the bias, since basing the difference alone could be insufficient. So we need to look at the ranks, and we'll go over that in a bit. And this because that just calculating probability difference strongly depends on how the language model assigns probability. So for example, in one case, probability distribution could be uniform, and then this would lead to a smaller probability difference. And in one case, you might think that smaller probability difference means it's less biased, but it could actually be that everything is just uniform, which could lead to bad results. So we also have a second metric we define for each token. It's the complementary reciprocal rank. And this is the difference between the reciprocal rank of the predicted token and the reciprocal rank of the masked token. And we define the CRR for the utterance same way. We take the average. And one thing to note is the CRR is used because it's unaffected by differences in the output probability distribution of the probability difference because we're calculating rank. So having these two different metrics helps to resolve some of the issues that might come by just using each one singularly. So we run the bias of the language models, or calculate bias of the language models by calculating mean absolute error and by calculating mean squared error of both probability and complementary reciprocal rank measured on each of the corpora. So these results are obtained through fill in the blank task with different language models. So we have a symbol signifies that the African American English and Standard American English are statistically significant according to Welch's two-tailed t-test, where the p-value is less than 0.05. And we also have a column to show the effects of the size according to Cohen's d. Yeah, so we'll go over some of the results, which were quite interesting. So one of the first results we thought was very interesting is BERT and DistilBERT, both in cased and uncased, showed a bias towards spoken American English for all metrics. So it was very clear that BERT and DistilBERT were both heavily biased towards spoken American English. And another thing is interesting is DistilBERT and both DistilBERT and distilled RoBERTa, so the distilled language models that we tested in this paper, they performed better with regards to average probability difference. So the probability difference was much lower compared to the non-distilled version. And this is a bit strange, perhaps because the distilled version achieves only 97% performance on the original task. However, there's been previous research that suggested that distilled language models sometimes exceed the performance of the original models, BERT and RoBERTa. So this can be in line with some of the previous research that's been studied on different language models, but something very interesting to note that these distilled versions seem to perform better in terms of bias. And thirdly, BART, despite having a very good prediction quality for African American English, shows the opposite trend with respect to BERT and DistilBERT. So it leans very heavily towards African American English with respect to all metrics that we measured. And this may be attributed to the type of data sets they were trained on, such as open web text. And this includes content scraped from Reddit, which may contain less spoken American English and may align closer to African American English. So further study can be done on how the corpora that's used to train these large language models affects the bias, because it's possible that by exposing or not exposing these types of different dialects of English, that the model will perform better or worse on these things. So furthermore, we analyze bias by graphing the difference of the empirical cumulative distribution functions of the probability difference of the utterances of SAE from AAE. So here we can see which models are less biased, which are distilled ones, and we found that BART leans heavily and RoBERTa lean heavily towards African American English, whereas BERT leans towards more spoken American English. So just another way to visualize sort of differences that occur from each of these two models. So furthermore, we studied the bias on African American features. So in order to investigate further, we look at how the results change when we acknowledge lexical, syntactical, morphological, and phonological rules of African American English. So in particular, we focus on double negatives, usage of the verb be, and contractions of words and groups of words, which we covered earlier in the presentation. And to do so, we filter for the above rules, and we randomly choose 50 utterances per rule and build a ground truth data set by manually translating African American English to spoken American English. And we repeat the mass language modeling experiments on these 150 utterances. And as you'll see in a bit, according to Cohen's classification, there's a prevalent medium effect for both of the metrics, with the exception of mean squared error for complementary reciprocal rank for the verb be case, where it's large. So in here, something that's very interesting that we found is that the translated versions are much better predicted with respect to African American English, surprisingly, for all 7 language models. And this is very surprising because even the models that were biased towards African American English performed better when we tested on these spoken ones, or manually translated ones on these 3 very particular rules. And this may be attributed to because that the African American English, it may be harder to recognize inside of the different data sets because there's less options for those particular rules, which are very different than spoken American English. And we also observed that for the translated utterances in the double negative class, that all 4 metrics are smaller and a sign of better performance than those measured for the SAE corpus, which is very unexpected, as we covered before, since RoBERTa and BART showed a bias towards AAE. But another possible explanation besides just that these are harder to capture inside the corpus is, and therefore the model is that the SAE corpus is collected from conversations from people with different regional origins, so from all over the US. And when we made the manual translations to convert African American English to Standard American English, we did not try to excessively standardize it, but it's possible by generating these sentences that are free from these regional biases that exist in the Santa Barbara dataset, that's more cleaner than those found in spoken American English corpus, and therefore it performs much better in relation. Yeah, so in conclusion, this work proposes a methodology for evaluating the fairness of transformer-based language models, specifically for African American English and spoken American English. And by directly querying these underlying mass language models in 7 different language models, we studied the quality of the bias of the predictions from several different angles. And we found that very popular state-of-the-art language models like BERT and DistilBERT show non-negligible bias towards Standard American English, with the quality of predictions being up to 21% more accurate than African American English. And in contrast, BART, RoBERTa, and distilled RoBERTa exhibit the opposite effect. And these leaned heavily more towards African American English. So additionally, our experiments also revealed that these distilled variants of BERT and RoBERTa are among the fairest among the 7 tested language models, which is very interesting that the distilled versions of these language models performed much better than their larger counterparts that they were trained on. So I think there's many different avenues for future work in this paper or in this research direction. So one question we have is, can fairer predictions of the outcomes be achieved with the ensemble learner of language models embedding opposite bias? For instance, if we have an ensemble of BERT case, which is leans towards SAE, and BART, which is AAE, will it perform better? Another is, given the insights from our results, can this bias be consistently mitigated with more inclusive corpora by taking into account African American English features? So by studying what type of corpora we use, if we include more of these examples of African American English with double negatives and contractions and such, can this bias be reduced? And lastly, there can also be special care put into the analysis of these distilled language models and understanding the cause which leads them to fair predictions with respect to the teacher model, and with a particular emphasis on web-based corpora used for training. Yeah, so that's it. Thanks to everyone for your time, and available for any questions.
Thank you. So, any question in the room? Yeah, François.
So here you were using the stuff for predicting masked words, right? But so, I mean, can you attack the problem differently if somebody speaks? Can you determine what ethnicity or cultural group he or she belongs to?
Yeah, I think it should be possible if you collected enough data. And in our example of the reason why we used mass language models is because we focus particularly on spoken language where a word might be missing. But I think if you see in the context words surrounding the masked word, that you find that there's a bias or the speaker tends to use African American English, for example, then that speaker may be African American English user, and that can be taken into account. So I think it should be possible based on, I guess, if the African American features are the context words rather than the masked words, that it should be able to be determined whether or not that speaker is African American English speaker or spoken American English speaker.
And does there exist like a database of the ways English is spoken by whatever types of groups in the world? I mean, because here you identify one class, but you may ask how many classes exist. And I guess if you want to determine where you are from, just from spoken English or spoken whatever, is it something feasible?
I think for if I know there are different corpora for different types of speakers. So for example, in the UK, of course, there's a different type of English spoken than in America, as well as they have their own version of mixed Black English that's spoken, which is very different than African American English in the US. So I think you can start to build these corpora and take them to account. But as far as I'm aware, there hasn't been any study that tries to look into these regional biases in order to determine where that user might be from. But I think it should be possible given that there are several different corpora that already exist for these different types of English-speaking groups.
And same question for generation. I mean, I guess even within a class like this one that you studied, I suppose, I mean, English is spoken if you are in your 20s or if you are in your 60s, might not be the same. Can you determine the age of a locutor based on the African American English he or she speaks?
I'm not sure if, at least with from the corpora that we used, which we found is like the only large amount of African American English. There's only 48 speakers, so I don't know if there's enough data there to determine the differences that might occur with age, just because we don't have a very large enough sample size to determine whether or not that speaker might be African American English speaker in their 60s versus their 20s. But yeah.
Okay, but if you had large enough a data set, would that be at hand or?
I suppose if we found that there was a large enough difference, I guess we'd have to analyze further whether or not there's like a significant difference in the way these different age groups speak, which may be true because, of course, younger generations use different English words and different slang compared to older generations. So I guess in theory, it can be possible. I guess in one case, I'm thinking maybe not necessarily African American English in particular, but even spoken American English today is much different than what was spoken, say, 100 years ago in terms of what sort of words are very common. So I think it can be possible in order to determine based on the sentence that someone uses.
Thank you.
Was your question? Yeah.
With regards to the first problem that you mentioned, with the blank filling thing that you showed us, with the problems related to Muslims. So this problem does not come from any specific corpora. So I'm guessing probably if you use the AAE or SAE, this problem might be still prominent. So what's the solution for like biased ideas that don't come from any specific language-based, corporas, or they're not based on language. They're based on, I don't know, some culture or some ideology.
Yeah, definitely. So I know this has been a very well-studied problem, I guess, starting to become a hotter topic, especially with ChatGPT and this stuff being more utilized in the real world. So I know, at least for in order to change GPT-3 to 3.5, one of the major updates they used was reinforcement learning with human feedback. So then they had people train a reward model, and they manually selected which sort of preferences they had between two different prompts in order to push the language model to align more with human preferences. And they found that by doing that, the model was significantly less toxic than here. Although it didn't significantly push the bias in all aspects, I think it significantly reduced toxicity. So I think methods such as that can be further explored in order to reduce these problems. But of course, I think it in some ways can hamper the language model. So for example, ChatGPT may be like too polite sometimes and just says, give very like too neutral of a response. So I think it's a topic that's still being explored, but I know that aligning it more towards human preferences has shown to significantly reduce toxicity, for example.
Other question, Leonardo?
I have a question actually in line with still this topic, because I mean, I was wondering, isn't this kind of this particular kind of language bias kind of due to the representation bias? Because I mean, if you train a model with the data that it is available, you have news, so you have a certain representation of the reality, and that corresponds to this kind of bias. So isn't data curation like the easiest approach to get rid of that? I mean, it's not the fault of us as individuals if society misrepresent this kind of things. So like minorities overrepresented in the bias just because, I don't know, if you are from a poor class, it's more likely that you commit like theft or this kind of need crimes, because it's not a crime because you are a criminal, but maybe because you are in a condition of need, right? So those minorities overrepresented, and the majorities being by definition normal, they are kind of spread out. Is it part of the problem?
Yeah, I think for sure that's part of the problem. So I think in this case, for at least for GPT-3, it was trained mostly on like American and like Western sources, and I think at least in the Western world, there's been more towards a bias, negative bias towards Muslims versus some other groups of people. So I think, of course, that the data that's being collected and subsequently trained on will inhibit these discriminations. So I guess this paper, in a way, maybe doesn't necessarily solve the issue of bias inside these language models, but rather gives a way to analyze, particularly for two different regional dialects, of like how to quantify the bias between these two different models. And then I think further research can work on methods to solve these biases, and then use the metrics we defined in this paper in order to quantify how well they're performing.
Thanks. And I actually have another question. You mentioned before that even speech systems are also trained using the same text-based data sets, base corpora available. but this means that you kind of encode the syntactic structures of languages, right? So the syntax, the vocabulary, etc. But they don't include any kind of phonetics at all. So is it so simple, the passage from text to speech?
Yeah, I think this is one interesting point that's been brought up, and I think in our case, the one interesting thing, of course, it's much more difficult to collect spoken data sets to train a large language model on, because that information is not widely available to and as easy to collect versus text, which is very readily available. But I think, therefore, I guess for any sorts of spoken model or agents, they will be trained on these models trained on text, which of course is encoded significantly differently than spoken text, of course, but I think that we show that how these models perform on spoken text is also interesting, because this is how they will be used in the real world. You know, like Alexa or Siri will be trained on this text data. So how well they perform on spoken tasks, I think, is also something that's very relevant.
Was there a question in the room? On the bridge? So thank you again.
Okay, yeah, thank you very much, everyone.